All right, so last time we started talking about stoichiometry, and we did a conversion, a multimole conversion, starting with aluminum. We were given 0.429 moles of aluminum, and we were converting it to iodine. And we learned how to use the chemical formulas and equations to basically convert moles of aluminum to moles of iodine using what's called the molar ratio, and that's a different conversion factor we can get from the balanced chemical equation. And so we're going to do some more problems, stoichiometry problems, and we left off last time where I showed you this little flow chart here, and it's showing you basically sort of the layout of different types of conversions going from moles of one substance to moles of different substance using the molar ratio. Then you can also go, if you don't have moles of something, if you have the mass of a substance A, you can go from mass of substance A to moles of substance A using a molar mass. Okay, and so you can go from mass of aluminum to moles of aluminum to moles of iodine, and then moles of iodine to mass of iodine using molar mass if that's what they want. And these branches out here, these are conversions we've already learned previously. We know we can convert moles to molecules or molecules to moles using Avogadro's number, so you can do that at any point where you're talking about aluminum, for example, or iodine. And then if you want to find the volume of a substance, if you know the density of the substance and the mass, you can find the volume. And so that's what I've added here and here as well. And so this is the overall scheme of stoichiometry conversions. You notice there's only there's more than two different conversion factors, but for the most part, most of the time you're only going to be using molar ratio or molar mass. And you just have to remember, if you're going from moles to molecules, you use Avogadro's number. And rarely do they ask for the volume of the substance, but if they do, then that's when you would use density in order to do that. Okay, so we're going to start with example 4.9 from your textbook. They give you the number of moles. They have 0.75 moles of propane, and they're asking how many molecules of carbon dioxide. Okay, so here's a balanced equation they gave us. What I like to do most of the time when they give us a balanced equation is go ahead and write what I have. And so I have 0.75 moles of propane here, and then I'm asked for molecules of CO2. So molecules of CO2 for this guy. Alright, so I can kind of just ignore the other stuff, okay? I'm just really focused on these two chemical species here. Alright, so the first thing I'm going to do is going to write what I'm given, so 0.75 moles of propane over 1. And then I have some conversion factor, right? So we need to kind of think about where we're going here. So we're going from moles of propane to molecules of CO2. Well, I can't do that in one step. So let's bring back our flow chart here. So I'm starting out with moles of A. Okay, we'll call this moles of propane. And I'm wanting to go from moles of propane to molecules of CO2. So first I have to convert moles of propane to molecules, or moles of CO2, and then I can go to molecules, okay? I can't do it in one step. So I need to go from moles of one thing to moles of another, and then I can go to molecules. Alright, so I'm going to go from moles of propane to moles of CO2 using what's called my molar ratio. I get from the balanced chemical equation. We can verify here quickly that they did give us a balanced equation. Here I have 3 carbon atoms on both sides. I have 8 hydrogen atoms. I have 10 oxygen atoms. Okay, so now I'm just going to write my molar ratio conversion factor here. And so I'm looking at my units, moles of propane. So I need moles of propane down here so the units cancel. All right, so here I have nothing in front of propane, so that means I have 1 mole. So if you have nothing written, no number written there, that means it's a coefficient of 1. So 1 mole of propane is needed to produce 3 moles of carbon dioxide. So 3 moles of CO2. All right, so my units here are going to cancel for moles of propane. Now I have moles of carbon dioxide. Now I need to convert moles of carbon dioxide to molecules of carbon dioxide using Avogadro's number. So 1 mole of CO2 is equal to Avogadro's number, 6.02 times 10 to the 23rd. Okay, and so I set up my equation and then I do my calculation. Alright, so I multiply my numerators together, 0.75 times 3 times 6.02 times 10 to the 23rd, and I get 1.35 times 10 to the 24th molecules of CO2. And so since I started out with 2 sig figs here, I'm going to go ahead and round it to 1.4 times 10 to the 24th power, and that's of course molecules of CO2. Alright, so here's another example, example 4.10 from your textbook, and here they give us another balanced equation. They're wanting the mass of sodium hydroxide needed to produce 16 grams of magnesium hydroxide. And so we're starting out with mass of a substance, and we also need the mass of a reactant. So this one's going to be a long problem. So if we look back at our flow chart here, we're starting out with the mass of a substance. Okay, I guess we could start here if you wanted to. Either way. So the mass of a substance, magnesium hydroxide, and we need to go from the mass of magnesium hydroxide to the mass of sodium hydroxide. So I need to go from the mass of magnesium hydroxide to the moles of magnesium hydroxide using molar mass. And then moles of magnesium hydroxide to moles of sodium hydroxide using molar ratio. That's what we get from the chemical equation. And then moles of sodium hydroxide to mass of sodium hydroxide, again using molar mass. Alright, so back to our equation here. What I'm going to do is I'm going to go ahead and start out with what's given to me, right, as a fraction. So 16 grams of magnesium hydroxide over 1. Okay, so I'm converting mass to moles here using molar mass. So that's a calculation I have to do. Okay, so remember, it's number of atoms times its average atomic mass, or in this case it will be molar mass. So for magnesium, that's 24.31, 24.31. And then for oxygen, it's going, there's 2 there. Remember, you have to distribute that 2 to both elements within the parentheses there. So it's going to be 2 times 16, which is 32 even. And then hydrogen is going to be 1 for each atom. There's 2 atoms there. That's going to be 2. Okay, so I have to add up my values here. And that is a 58.31 grams per mole. So basically I have to derive my conversion factor for my molar mass for my compound magnesium hydroxide. So it's 58.31 grams per mole. So that's what I'm putting here. So here my units are grams of magnesium hydroxide, so I need grams at the bottom. So 58.31 grams of magnesium hydroxide is equal to 1 mole of magnesium hydroxide. Alright, so now I've gone from grams to moles of magnesium hydroxide. I need to go from moles of magnesium hydroxide to moles of sodium hydroxide using molar mass. So here I'm getting it from my chemical equation. Here I have moles of magnesium hydroxide, so here there's a 1 there, so for every 1 mole of magnesium hydroxide produced, I I need 2 moles of sodium hydroxide. So 2 moles of sodium hydroxide. Alright, so now my moles of magnesium hydroxide cancels out. Alright, and I have moles of sodium hydroxide. Alright, so now I need to go from moles of sodium hydroxide to mass of sodium hydroxide, again using molar mass. So I have to, again, derive that by just adding up the molar masses for each element. And depending also, it's based off the atomic masses too. So, alright, so I have sodium hydroxide. So for sodium, there's 1 atom of sodium, and its molar mass is, I'm going to round it to 23, it's 22.99, I round it to 23. And for oxygen, there's 1 atom there, and it's 16. Okay. And then for hydrogen, there's 1 atom there, so it's just 1. So I add these up, and I get 40 grams per mole. Alright, so now I can go ahead and put it in here. So for every 1 mole of sodium hydroxide, it's 40 grams. Okay, so here I went from mass of magnesium hydroxide to moles of magnesium hydroxide using molar mass, and then moles of magnesium hydroxide to moles of sodium hydroxide using my molar ratio from my balanced chemical equation, and then moles of sodium hydroxide to mass of sodium hydroxide using molar mass. So when you have what I refer to this as a mass-to-mass problem, you're given the mass of one substance, you're having to find the mass of another. It's a 3-step problem, right? You have to, 2 of those steps you're using molar mass, and then the one in the middle is using molar ratio. Okay, so no matter what you're doing, when you're doing a mass-to-mass problem, this is sort of basically how you're going to set it up. You use molar mass first, and then molar ratio, and then molar mass again. And if you don't know how to do that, if you just look at the units kind of tell you what you need to do, right? It tells you the units you need to start off with, and then you know you're going to have to figure out how you're going. And so if you look at the overall scheme here, you see that sort of the moles are sort of the middleman. You know, you have to have moles in order to convert mass of one thing to mass of the other. You have to have moles if you're going from, if you're starting out with mass and you're wanting molecules, you still have to go through the mole. Okay, just keep that in mind. This is really what you have to memorize. Okay, this flow chart. And if you just remember you just really have 2 main conversion factors here: molar ratio and molar mass. If you remember the molar mass, the units for molar mass are in grams per mole. And units for molar ratio, it's moles of A to moles of B. Alright? And then molar mass is grams per mole again. So if you're going from moles of one thing to mole of the other, it's molar ratio. Moles of one thing to mass of the other, or mass to moles, then you're using molar mass. Alright, so here now we're having to do the calculations here. So all we're doing here is multiplying fractions out. We're multiplying again the numerators together, so even though the units are canceling out, the numbers are not. So 16 times 1 times 2 times 40, and that is 1,280 over 1 times 58.31 times 1 times 1, which is 58.31. Okay, and so this is a comma, by the way. So that's going to be 21.95. Okay, and so I would call this basically 22.0, and that is going to be mass, G, of sodium hydroxide. So 22 grams. Alright, so next we have example 4.9, where we have 0.75 moles of propane given to us. They're asking us how many molecules of CO2. Nope. Sorry, wrong I grabbed the wrong paper here. Here we go, 411. All right, so 411, we have a balanced chemical equation again. They're giving us the mass of propane, and we need the mass of O2. All right, so here we're starting out with 702 grams of propane. Okay, so we need to go from the mass of propane to moles of propane first, okay, and then go from moles of propane to moles of O2, and then moles of O2 to mass of O2. So this problem is similar to what we just did. So again, let's look at our flow chart here. We're going from the mass of propane to the moles of propane using molar mass, and moles of propane to moles of what are we doing? O2 using molar ratio, and then moles of O2 to mass of O2 using molar mass. So very similar, especially the same problem we did previously. And so here we need to find the molar mass of propane. All right, so I have to calculate that again like I did before. So for carbon, we have 8 carbon atoms times 12. Okay, and then for hydrogen, we have 18 hydrogen atoms times 1.